Okay, so we are on time. Please take a seat if you're not sitting, and welcome, William.
Hey, everybody. Thank you for staying so late for my talk. I know it's pretty late, so I appreciate it. Today I want to talk a little bit about a tool that I built a couple months ago called zizmor, and how I've been using it to hunt for GitHub Actions bugs and how you can use it as well. So just a little bit about myself. My name is William. That's my website. Currently I'm an engineering director at Trail of Bits, but this is not a work talk, and these slides nor my opinions that I express throughout them are the opinions of my employer. And outside of work, I'm also a maintainer of Homebrew, as well as a member of PyPA, and a contributor to PyPI and a few other things. So you'll see me possibly make reference to some of those. And then if you want, that QR code has these slides. And so if you want to follow along, there's some parts where you can try in real time the things I'm going to show you, so you can try to exploit them yourself. But actually, let's skip that. So let me do an intro to GitHub Actions. I figure probably, actually a quick show of hands, how many people have used GitHub Actions in this room? Okay, overwhelming majority. So I'm not going to do too much of a intro. But basic version, it's GitHub CI/CD offering. It's free for open source. It costs money otherwise. It's a bunch of YAML hell. Workflows are sort of top-level units of execution. They contain jobs. Jobs run on VMs. VMs contain jobs that have steps, and each step is an independent sequence of shell commands or recomposed actions, which contain themselves other actions or shell commands. These can be checked out from other repos. So actions checkout actually checks out the actions checkout repo and runs code from that repo. Those actions themselves are also YAML hell. They define reusable operations that you can share between repositories. There are official ones, which are generally under the actions namespace, as well as third-party ones, any public or private repo on GitHub, as well as local actions, as in you can call an action that is defined somewhere in your own repository if you have it checked out within your job. These have full generality. They can run code, they can run other actions, etc. And importantly, they run in the context of the job that executes them, meaning that any secrets, credentials, etc., that you give that job, the action also has. And also, sort of importantly, as we'll see later, they have full access to the job's runner state, which includes the file system, which contains all kinds of interesting and useful things, as well as other processes running on that VM. So bottom line, GitHub Actions are arbitrary code execution as a service. That will come up in various important ways throughout this talk. It's a very powerful system, GitHub Actions. GitHub Actions, it plugs into the broader sort of permissions model that GitHub offers. Every workflow runs with a latent secrets GitHub token or GitHub token, depending on the context you're in. And by default, unless you opt into a more secure mode, this token has a lot of powers, including modifying the repo contents of the workflow, of the repo that contains the workflow that is loaded with it. If you are a workflow author, you can also up or down scope this credential at the workflow job or step level with permissions blocks, which tell that scope of action how many credentials it has, which it can't exceed with that default token. However, there's sort of some wonky behavior there, where permissions are inherited from parent job or workflow contexts if they're not set. But if they're explicitly set, they're shadowed. So they're not telescoping, they're shadowing semantics. And again, this comes up in important ways. So of course, you can do things like on the right, where you have explicit read, write, or none permissions for each sort of scope, or you can set read all or write all, or you can do an empty object, which means give me no permissions at all. However, that still produces a token. That token just gives you sort of larger rate limits versus not having a token. Another way in which GitHub Actions is extremely powerful, which again will come up when we talk about the security aspects of all of this, is that it has this extremely powerful expression system. Most parts of the workflow or action definition scheme in YAML support expressions, which are defined via this like curly syntax where you put an expression in the middle. Sometimes you don't need those curly, such as in an if condition. These expressions have a lot of functionality within them. They can do math, they have control flow, they can encode and decode JSON, they can call a set of functions that are defined within the runner itself, etc. They can also directly, or rather, when you expand them, they expand directly into whatever context references them. So an if condition, an end block, a with input, or even a run body, which contains, obviously, shell script that you're trying to run. You can expand values directly into that shell script. At the core of the expression system are these things that GitHub calls contexts, which are really just JSON objects. When the runner is invoked, it is loaded with a set of contexts, and you can access those contexts sort of as if they were like JavaScript objects. So if you have a nested dictionary that has like secrets.GitHub token, that gets modeled as the context, secrets.github token, in the expression syntax. And these contexts come from both static and dynamic sources. So the static source is something that you define sort of ahead of time for the runner to load. So that's things like the runner's configuration, as well as GitHub side state, so the event name, the event payload trigger that triggered the workflow. And then dynamic is things like matrix expansions. Okay, I realize I have way more stuff than I thought, so I'm going to kind of breeze through this. Even more powerful, you have these special variables. You can set environment variables, you can set the path, you can set variables between steps, and you can also set step summaries. There's also a special file system state, like event path and tool cache, and these are, again, useful in ways we'll see. So now let's talk about the security of all of that. So before I do that, why does any of this matter? Well, one answer is it's wildly popular and it does everything. It's the default choice for GitHub, meaning that millions of people use it. Pretty much everybody in this room uses it. As a corollary, it's used by developers with huge skill ranges, meaning that people who just want to get something done are using it the same way that people who are experts in CI/CD deployment. And it has this massive range of uses, including, most interestingly to me, people publish to PyPI, et cetera, using GitHub Actions, which means that the security of their package on those indices directly mirrors the security of the system that publishes them. So millions of users plus a really powerful and complex feature system means security fails. So let's break some of this stuff. Okay. Crowd question. Find the vulnerability in this. What's the issue? Anybody know? Yep. Okay. Template expansion, right? What we're doing is we're expanding the value of GitHub event pull request title directly into the shell context, which of course I can give it hello, semicolon, cat password, and now I'm running arbitrary code. So again, the core thing here is this is something that the attacker controls. The title is an attacker control value that is loaded. Anybody can create a pull request on a public repository. If you put your title as hello, semicolon, cat password, you're now running code in the context of the workflow that triggered it. That's baby steps. Okay, what about this one? We've quoted it this time. Does anybody see the problem? It's the same vulnerability. It's the same damn vulnerability. And the reason for this is going back to expressions. Expressions do not care about shell level quoting. Because they're injected by the actions runner before any shell processing happens, they are injected, there's no chance for the shell to reparse what you've injected. It's exactly the same thing as SQL injection. You can quote as much as you want in SQL injection, but if you're directly injecting the value, you can always inject an escape to the escaping. So in this case, our payload would be hello, quote, payload. And we get the exact same thing. So this is baby steps. Okay. Anybody see the vulnerability here? Okay, that's enough time. So it's nothing about any of the steps. All the steps are semantically correct. However, what happens is actions checkout, that step we call it there, the first one, it persists silently at the GitHub token by default. So when you run actions checkout, that context token that you use gets stored in .git config in the repo that you check out. Then, when you run actions build upload artifact with the current directory as the path, you have now persisted your credential to a public artifact, meaning that anybody who goes to download that artifact now has your credential. That credential is only alive for about 4 hours, if I remember correctly, but for 4 hours you've now leaked potentially a global write credential for your repository. Okay, still baby steps. They fixed this, by the way, but they fixed it by not patching checkout, but by patching upload artifact to ignore .files, which broke Python coverage. Okay, getting a little bit more interesting. Anybody see the bug in this one? You'll notice that we are no longer doing environment expression injection. We're now forwarding via an environment variable. So there's no more injection vulnerability there. Okay. Like I said, GitHub environment is one of those special variables. It's a file, but it's just a file, nothing special. However, we can write multiple lines to it at once. So in this case, if a user or an attacker submits a title that matches that expression before, that expression, because it uses the, I believe it's the P flag, it prints multiple times, once for each match. So in this case, we've injected 2 variables when we meant to only inject 1. We've injected message equals foo and also ld preload equals hackme.so. And so now if you can if you have write access to a runner, even if you don't have execute access, you've turned your write access into execute access, because ld preload will run in front of any binary that gets executed. So there you go. Okay, let's get a little bit more advanced. GitHub Actions has services and APIs and actions for saving and restoring caches. These are used and are critical for speeding up actions that pull a lot of things from public indices. these caches are keyed, and it can be restored based on partial key matches. So for example, if you have your Rust dependencies, you want to restore from multiple different sources if you unfold from multiple places. And the way it restores when you have partial matches is it restores based on that partial match, but also sort of a privilege system of anything that's previously been landed in the upstream repo. So if you can poison that upstream cache, any downstream workflows that run will run with your poison cache. So here's the question: like, how does GitHub know which branch a cache restoration should come from? Well, the answer is the branch name is an implicit part of the cache key, and it's computed on the client side. How does GitHub Actions authenticate cache stores? Stores are authenticated with an Actions runtime token, which is injected into the runner, separate from the GitHub token. Combined, this is the perfect recipe for cache poisoning. We have the credential we need to inject cache entries, and we have a client-side controlled cache prefix, which we can tell the Actions cache service to cache with. There's no authenticated domain separation, in other words, between branches, which is hard to do because you would need then a way to do like delegated authority between branches, meaning that branches can collaborate with each other's caches. And all workflows in the repo that run with the repo's permissions have that Actions runtime token, which means that even a very, very weak workflow, one that has empty permissions, still has that cache token. And it's valid for 6 hours, which means it's not invalidated by run or teardown, which means you have 6 hours to effect your cache poisoning attack. So this was kind of my spoiled by the previous session, but Ultralytics is the perfect case study for this. Really popular machine learning vision model, 68 million downloads from PyPI, and they have many CI/CD operations that are intermediated by a bot account. Spot the vulnerability. It's the exact same one. It's our baby step vulnerability. They inject directly into the shell context with the user-controlled variable. This is happening with a pull request target trigger, which, unlike a pull request, runs with the upstream repo's permissions. So they've given this attacker upstream repo token permissions. The attacker sends a pull request with that title, which runs this payload, steals the cache token, and goes on to smash the cache with a bunch of entries, one of which eventually causes a malicious PyPI upload. So what's cool about this is that they didn't steal, well, later on they steal, but at first they didn't even steal the PyPI upload token. What they did was they poisoned the artifact that was used to produce the upload token. So this isn't visible from PyPI's system. So they do this, right? But what's great is, and the release is done fully on CI with a push event, meaning that it was pretty hard to notice until someone actually noticed the malware in their system. But, Ultralytics responds, mission accomplished. They have deleted they have, triage and everything. Several days later, it happens again. And the reason for this is that even though they fixed the actual cache poisoning vulnerability and the permissions, the insecure trigger they used, they did not revoke their old credentials. And so the attacker just stole the old credentials, which they never revoked, and did it again. So after you've been owned on GitHub Actions, please revoke your credentials. Okay, I don't have enough time for these takeaways. Please look at the slides. Okay, now I actually want to talk about the talk, which is hunting for bugs with zizmor. So demo time. You can do this yourself if you want, but here is zizmor. I'm going to run it without online audits because the Wi-Fi is kind of slow, and I'm going to run it against the 2 repos that the Ultralytics attack was on, and it's pretty fast. And there we go. This is just every case where the attacker could have injected. They only needed one of these, but it's not so good. Okay, technical details. zizmor is a typical audit tool architecture. It has a preparation phase, an operation phase, an aggregation phase, and then the output is like this Rust-C style diagnostic, where it'll tell you what span caused the vulnerability. Individual zizmor audits are implementations of this audit trait, has sort of standard stuff, and then there's various ways you can define an audit. It can be over a workflow, a composite action, or the individual steps or jobs within a workflow if you only need that level of granularity. There's actually a new one too. There's audit raw, which can give the raw input to as a string if you need to do just like basic, really, really, really basic regex matching. Oh, that's big enough. Good. Okay, so that's an entire audit. They can be really small. This one's a secret inherits audit. All it does, it looks for places where a reusable workflow uses secrets inherit, which means it inherits the entire secrets context rather than being given a specific set of secrets, meaning it violates the principle of least authority. And then you can also do multiple locations per finding. So you can say like this step calls this action with this set of subfields, and that's why it produces such a nice sort of spanning representation on the command line. And yeah, if you want to contribute, these audits are good examples of things to start learning how to write zizmor audits. Some technical challenges. Like I said, it's all YAML hell under the hood. So one of the questions is, how do we model GitHub's complicated workflow and action contents? It's an extremely large JSON schema that's public, but it's very large and complicated. And codegen support is limited in Rust for JSON schema. Solution is we have this GitHub Actions models crate, which has handwritten data models for every single part of GitHub Actions, which we then use to generate those spans for YAML spanning back to the source. And then that follows the next question, which is, how do we turn these symbolic YAML contents, like this step, back into a span that we render to the user? And the answer is, well, we couldn't with, there's no real span preserving YAML parser for Rust, and also sort of YAML is deprecated, which it still is, and we still depend on it. But we wrote YAML path, which concretizes that abstract path, like job test steps, zero name, back into a source level syntax span for pretty rendering. Okay, takeaways. Stuff's complicated, has numerous security footguns, and most users are normal devs, and they should not be expected to know these things. You shouldn't have to know that GitHub has no sort of permission separation between branches to use caches securely, meaning that they're extra susceptible to insecure defaults. Moreover, offensive security research into GitHub Actions is still pretty new as a field. Really, the first visible public efforts into this stuff started around 2021, and new attacks and techniques are still being discovered. For example, the cache poisoning attack was just last summer. And so, even though I've talked about some of this stuff, it's not anywhere close to the end-all, or will be close to the end-all of action security. And yeah, I said that. It's also simultaneously kind of easy to analyze because it is just YAML, and also very difficult to analyze because there's extremely dynamic inputs like contexts, which can be loaded with pretty much anything, including dynamic matrices that get loaded at runtime. So those kind of things are very difficult to analyze, and we try our best. And as part of that, we detect many security pitfalls, but not with perfect fidelity. And this is in part because of design choices, for example, favoring offline auditing where possible, but also because of that fundamental dynamism. It sort of models normal computer static analysis. You can't do certain things because the program is dynamic and you're static. Okay, so I sped run all that so I could have some time for questions. Thank you all very much for listening. If you want, slides are here. All right. Yes?
Thank you, very nice talk. I have two kind of questions, but they are more or less the same. So, nice tool to use in command line, but I have hundreds and hundreds of pipelines, so I want to automate this in my pipelines. Any thoughts? Could I do it inside my runners, or could I have normal action that I run to check the workflow itself?
Yes.
Like exception thing?
Yeah, so the question was, can I use this in my pipeline? And the answer is yes. So I showed the human output. There's also a Serif output that integrates directly into GitHub. And so you can see on GitHub a UI render of these findings.
Okay, and then you run the CLI in your pipeline?
Yes, exactly. Yeah. Yeah. Yeah, Homebrew uses it, so you can use Homebrew as a reference point for using it in CI. Yes?
Sort of a variation of the same question, sorry for that.
Fine.
Could it be possible to write the same kind of audit rules using CodeQL, which is GitHub's own, and then it's super integrated?
Yeah, so the question was, can we rewrite the same kind of rules using GitHub's CodeQL feature? And the answer is they have. GitHub 2 weeks ago introduced beta support for GitHub Actions auditing with CodeQL. And I will say this, because I wrote this tool, CodeQL is a much better fundamental system than what I wrote. So if you want a system that is fundamentally built for static analysis, check it out. The downside is that it's CodeQL, it's big, it's complicated to integrate. So there's some trade-off there. Yes?
If you look at GitLab CI, that's all works very similar with this YAML files. Are the problems the same, or is it something like?
Yeah, the question was, is GitLab CI similar? And the answer is I have no idea. Maybe. I would love it if someone looked and sent me patches to support GitLab CI. Yes?
So the GitHub Actions APIs as well as the GitHub provided actions are, subject to regular updates. How do you plan on keeping up with those updates?
Yeah, so that's a fantastic question. The question is, how do we keep up to date with the latest changes to, for example, the official actions? My long-term plan is to have a static representation that we can upload via like an HTTP, put it on an HTTP server somewhere, have a static API that pulls it down. So if the default posture of an action changes, clients that don't want to update zizmor itself can fetch that and basically update the rules. currently it's baked into the binary. So currently, if Actions changes something fundamentally, which they haven't really yet, I have to send a new release to propagate it. Yeah. Yes, please contribute. Great. Thank you very much. Yeah.